Thank you so much for coming. It's such a great pleasure to have Professor Jef Caers today for this distinguished seminar. So Professor Jef Caers received both Master and PhD in mining engineering from Catholic University of Leuven, Belgium. Currently, he's a professor of Earth and Planetary Sciences at Stanford University. He has pioneered research on data science, AI, decision-making under uncertainty in developing Earth resources. He's the founder of Stanford Mineral X Consortium. He collaborates with the mineral exploration industry to reduce cost and improve discovery. He has authored 6 books on data science, decision-making that blend science with practical industrial application. He was awarded Cronbane Medal of International Association of Mathematical Geoscience for his career achievement. Please join me in welcoming Dr. Jef Caers.
Glad to be here. And it's a special seminar for me because my family-in-law is all the way in the back, and they're not scientists, so it's great to have that as well. As Haruko said, I'm a mining engineer by training. Graduated in '96, and then you came to Stanford and became professor of petroleum engineering because this was much more interesting for funding. But as fossil fuel funded research became less attractive, and because we changed to a sustainability school at Stanford, it's also a story here in this presentation. I joined a small startup company in the Bay Area called Cobalt Metals. At the time, it was a company of 10 people. And the premise of that company was to discover more mineral deposits using AI. And so that story has become an incredible success. So the company is now in the middle of starting one of the largest copper discoveries in Zambia, which has, if you look at the resources, about $200 billion of copper in it. So this is a significant achievement, number one, because it was done using not a mining company, a startup company. Secondly, the science that was used to do this was very different from the approaches in the mining industry. Particular mining industry doesn't know about Bayes or doesn't know about computation. It's all very heuristic and expert driven. And now starting this mine, which has broken ground about a week ago. And so that's the kind of story I'm going to tell because the reason I started Mineral X program is because one of my students, John Myrne, who graduated, and then as you see, he went work for Cobalt Metals, and he was one of the key implementers of the AI that did the discovery in Zambia. And so guess what? John now has his own company, left Cobalt after that period and started his own company called Terra AI. And so I'll talk about that in this talk, about this story of how this all came about. And it's not, of course, just an academic story. It's also a story of how rigorous science can actually have a huge impact into reality. So why is this all very important? Number one, if we look at the success of making discoveries around copper in particular, we see that if you would call success 100 in 1990, then we are now down to 10, basically only 10. So it means essentially that the amount of exploration dollars that are put in the industry are increasing while the discoveries are decreasing. And so we have to think a little bit about why that is. And there's a very good reason for that. The reason for that, if you look here in this graph around the critical minerals, particularly nickel, lithium, and copper, you see that this is the axis, right, from starting in almost 250 years ago, 150 years ago, all the way till today. You see here are all the discoveries and where they were discovered. And you see they're all discovered at the surface of the Earth because the deposit was outcropping at the surface. A few here are discovered were deeper. These are just accidents. So obviously these discoveries, these big discoveries of copper and lithium that are outcropping, they're mostly discovered. So we are now left with undercover. And that becomes very challenging because things like geological fieldwork rely on the fact that something is outcropping at the surface. So now you walk on an area where there's nothing, plants, and you're a geologist, and there's nothing there. So how do you discover those deposits? A little bit about exploration. So exploration is, I call it an exercise of reducing uncertainty from an extremely large scale, I think about Canada, to a borehole scale. In the end, you are going to make a discovery by drilling $1 million borehole in the ground and observing mineralization. So how do you get there? So there is a lot of geological work associated with that. You see, for example, that there are areas and belts that have a large potential. In this case, this is nickel. You see nickel mineral occurrences, right? You see one over here, a bunch over there. These are nickel mines. And so you can now rely on the data that is available, particularly in countries like Canada. They have very good data around geophysics, geochemistry, et cetera, and use machine learning to make predictions of potential areas of interest. And so one area of interest here is, for example, Raglan mine, which is over here, is a nickel mine. And so if you zoom in here and you look at the result of a machine learning exercise, then you get a map like this, right? And you see that indeed at that area, the potential for having a nickel deposit is yellow and the blue is no potential. The problem, however, with machine learning and deep learning approaches in the sense is that you see the scale observation here is that 1 pixel is 5 by 5 kilometers. And so you still need to go and look on the ground. Now, there's a problem because in this area, you only have no snow for 3 months. So how do you do exploration efficiently? So it's not just a matter of doing machine learning. You still need to get either on the ground. And once you go on the ground and you do here have some outcropping rocks, you may find some rocks with mineralization, but then you need to bring in drilling equipment. Bringing in drilling equipment from here requires flying 3 737s all the way up to there and then start drilling. You see the cost of that, right? It's a huge cost to do mineral exploration while there is essentially no income. And so one of the reasons is now that a lot of companies who do exploration, particularly in these minerals, are small companies. We call that junior mining companies. And they basically go one drill all at a time. They drill something, and then go back to the bank, drill something, go back to the bank. It's not an efficient way of doing exploration. So Colo Metal said, well, we're not doing that model. We have raised $500 million from venture capital. We can do this very differently. We can say, we are going to spend $30 million. We're spending several summers up there, and we do exploration in a Bayesian way, as opposed to doing it in a sort of trial and error way. So there are two main tasks. If you now look at it from a computer point of view, is that number one, as you see, we need to make predictions, right? We have data, we have lots of data, and we need to predictions of something of interest. But the bigger problem is to make decisions, which is, what do we do next? Right? Do we go on the ground and do surface geophysics? How do we do such surface geophysics? Or do we skip surface geophysics because we can rely on geochemistry, and then we have to think about boreholes and where we'll be drilling those boreholes, right? An ore body is about 500 meters big, so you can miss it easily. The geophysics that we acquire in the mining industry is typically magnetic, gravity, and other geophysics, but it's not as good as, say, seismic data in the oil and gas industry, and that's a big problem. So what happens a lot is that people drill and based on some kind of geophysical signal, but find nothing. False positive. One of the big problems in the industry is false positives. Drilling into anomalies, finding nothing, and doing it 10 times, finding nothing. Okay, so you could say, well, I'm a mathematician, I'm a computer scientist. That sounds like a problem I can solve. It's a problem of Bayesian experimental design. Is a design that says, or a metric that says, where would I take additional data to reduce uncertainty on some property of interest maximally, right? So if you want to find a volume of something, you can think about where were that drills so that you know as much as possible about that volume. This equation may look a little difficult, but the main part is over here, which is to do that, we have some prior uncertainty on our properties, and our data will then give us some posterior uncertainty. And so that ratio, of course, matters. If that ratio is 1, there's no informative information. But of course, we haven't acquired the data yet. That's why we need to integrate all the possible data outcomes in all possible models. So this idea has been around for a very long time. Was done by the paper in Lindley in 56. But this equation leaves a lot of questions if you go to practice, right? It's not a question just of how do we solve this equation with Monte Carlo simulation, but also what is theta? What is D? I mentioned in the previous slide, there's so many possible Ds. And if you've done that, what is an F? Right? And what are these factors? So these are becoming very important. So we're not going to start from this way. We're going to start from decision making. So in decision making, we're using a different metric than Bayesian optimal design. We're using a metric for what's called value of information. So value of information is a metric in dollars that quantifies whether you would acquire data and figure out whether that value of that data in dollars is larger than the cost of the data. So obviously you would never acquire data that costs more than its economic value. So, and the simplest possible thing is to look at an economic project like this, where everything is simple and binary. So let's say I have a project and I have a decision node here, which is that blue thing. And with that project, I can either walk away, right? And I have the walk away dollars, typically 0, right? If you walk away from a project, you haven't spent anything. Or you can go ahead and then you have to face an uncertainty, which is this circle, with a probability of success A, let's say it's binary, and you get dollars for A, or you get, if it's not A, you get fail dollars. So if you're not happy yet with these probabilities, and maybe the economic value, then you can do another thing, which is to say acquire data. Say I'm not doing any of these yet. I'm gonna give a third option, which is acquire some data, right? But we haven't acquired the data yet. Okay, so we're going to say, oh, the data could be this or the data could be that. Let's say in a very binary way, the data could indicate that A is positive, or the data could indicate that A is negative. And if you now go here, then we see, then we have to execute the project, right? After we acquire the data, we're going to have to execute the project. This is our project, right? This looks exactly the same as this. But you see now the probabilities have changed. So now we have a posterior probability of P of A given B, or not A given B, and the same over here. So to solve this problem, right, we just need to calculate the expected value of this, the expected value of that. So this is called then the posterior value of information. And this is the prior value of information. And so the value of information is the posterior value minus the prior value. So if the posterior value equals the prior value, then there's no value. If that posterior value minus the prior value is some dollar value that is less than the cost of the information, you will also not acquire the information. And so you can just use Bayes' rule, of course, to calculate P of A given B. P of A given B, you can calculate that with Bayes' rule. And if you solve that, you can come up with this equation here where you can calculate the prior value, which is the expected value, is the maximum between walking away and going ahead. The posterior value is then the maximum, but the prior value, and then the average of these values you create when you acquire data. So that's a nice framework. That's decision theory. There's a problem, however, when you're doing exploration, you're not worried about economics of the deposit. You're interested in finding a deposit. So why would I worry about economics? Also, the economics are very uncertain, right? Economics are a function of price, demand, all kinds of other factors that have nothing to do with exploration. So I decided to do it differently and call it another one, which I'm going to call efficacy of information. So efficacy information is a dollar less value of information, where you see we're replacing the dollars with ones and zeros and probabilities. So remember, this was the dollar value when you get a success, this dollar value when you say failure, and this is dollar value when you walk away. So the question is, would I bet on this project? Okay, so why do we not like that? Well, if you now look at the expected value, right, the expected value of the go ahead is P of A times 1, and the expected value of walk away is P of A. So you're walking away to another bet that has equal probability. So that means that the value of this project right now is 0. And so I would now need to take information in such a way that maybe this branch here gets now a value larger than 0. So I have no longer a cost. I don't do any of that. I just compare the expected value of this with the expected value of that. Yeah.
Why do you keep the value of walking away in a conditional setting to still be P of A?
Because I want to have the option of betting on this project or betting on an equivalent project. So this project, its expected value is also P of A.
I see.
Yeah.
I see. For which you don't have measurements.
Yes.
Okay.
Exactly.
Got it.
So I have measurements for this project. I don't have measurements for this project.
Got it.
So now you can do the same thing as we did, right? As we said, we can do the same thing. We can look at the prior value, which is P of A, or we can look at the posterior value, which is this equation. And then the EY, expected value of information, is the difference. Okay, let's do an exercise on that. So this was our kind of a first project. We are here in the northern part of Michigan. And there is a mine there called the Eagle Mine. They produce nickel. And this is a magmatic sulfide deposit. So this is basically an intrusion, which at the bottom contains nickel concentrations around 2%. So they're very attractive deposits because of very high nickel concentration. And so, yes, we see here on the magnetics an anomaly, right? So I'm going to now pretend that I'm arriving here. So a geophysicist had looked at this and said, oh, this is a very interesting anomaly. We believe there's a nickel concentration or intrusion there. Well, the only way to assess that is to drill, right? Then the question is, where would you drill? And if you're going to use some kind of a metric like value of information or efficacy information, you have to drill to get a certain objective, right? Is the objective to make a discovery? Is the objective determine the value? Is the objective determine the grade? Is the objective to calculate the reserves, right? So in decision science, we just state the objective, but here we have to actually know what the objective is, which is actually not that easy. Okay, so how do we start? We have the anomaly, and we do a Bayesian inversion of this magnetic data, and that Bayesian inversion gives us a whole ensemble of three-dimensional model of the intrusion. So here I have now hundreds and hundreds of models of the intrusion geometry, right? That is the uncertainty. So where would you now drill? Would you now drill in the middle, which is what all the companies do? Or would you drill on the side? That's the question. Okay. Most people say, let's drill right smack in there. Okay. Well, if I calculate the efficacy of information, what I'm going to do is I'm going to give myself a whole bunch of candidate boreholes. So these are all the boreholes that I may drill. Right. This is the mean of all the models. So you see, we're very certain in the middle. We're less certain on the outside. And so the efficacy information says the best borehole to drill that reduces uncertainty on the intrusion location the most is this red borehole, which is on the side. That makes sense, right? Because you would drill not where you're certain, you would drill where you're uncertain. That's not how companies do it, though.
But
Yeah.
so this is sort of conditioned on the prior information that you know there is certainty that you know there's a nickel for certain.
No, we're saying there is an intrusion.
I would see.
So that intrusion, we're not even knowing it contains nickel,
Uh-huh.
right? So that assumption is not unreasonable given the anomaly. The anomaly says there's quite a strong magmatic body. And so magmatic sulfides are rocks like gabbros and peridotites, which are definitely showing up on magmatic survey. And knowing the history of that area and the geology of that area, you are expecting that. That doesn't mean that there's always a false positive, but if we would assuming that it is a magmatic intrusion, where the magmatic susceptibility of the surrounding rock and the intrusions are different, then this would be the signal and the inversion. Yeah, a lot of assumptions.
Right.
We're not saying nickel.
Let's say, if you drill the side of this anomaly, there is a possibility that you don't see anything, right? The false positive, but
There is absolutely.
You take that
You
risk.
still have prior assumptions. Yeah.
You take that risk.
Yeah.
Nice. Okay. Thank you.
And then you update, right? You get a borehole. And so the borehole indeed finds some part of the intrusion. The borehole, however, will always look less smooth than the inversions. So the inversions, right, here are very smooth, right? Ore bodies are not like oil and gas reservoirs. They have, they have dikes, they have lots of concentration of metals that are very heterogeneously distributed. So when you drill a borehole, you get something very different. And so now you can update. So again, it's a new Bayesian inversion where you use the borehole and the geophysics, and you create a new posterior model. And then you can go on. And you can now recalculate the volume of the intrusion. Right? So we started out with a very wide volume because of the geophysics, lots of uncertainty. Once we drill one borehole, everything starts to reduce in uncertainty and very quickly reduce in uncertainty. And so you can go on like this. You can drill. Now you can think, I want to drill 3 boreholes. And now you see you're starting to drill some boreholes in the middle. And these are the 3 optimal boreholes, 1, 2, and 3. And you can go on like that. So this kind of form of planning in AI is called open loop planning. Open loop planning means that you are planning, you're executing, you're updating, and you plan.
Sorry, can you explain a little bit how you do this mean EOI thing?
So this is the equation, the EOI. There's a definition of that.
So, but these drill holes are geologically speaking better because you get information about the extent of the intrusion.
Yeah.
And you'll get something about the nickel thing. So if you go smack in the middle, you get only one information.
Yeah.
You wouldn't get, so that's,
Yeah.
Okay.
Yeah. So actually the efficacy of information of a borehole in the middle is probably something like that.
And because you just get.
Because we're drilling to reduce uncertainty.
Yeah.
Right?
Okay.
So mining companies don't drill like that.
Yeah.
Mining companies drill to get mineralization.
Yeah.
But that's not effective because then you end up after a while realizing that you have to go to the side to actually find where it ends.
Yeah.
So we're saying don't start like that. Don't start in the middle, start on the side, and then gradually go to the middle.
Want to go first, Laura?
Go ahead.
Okay. So hi, I work for Schlumberger. Our business is to drill these
Yeah.
holes and make
Yeah.
these measurements. And I totally get what you're saying. You want to drill where you're uncertain, not where you're more certain. But indeed, our clients, and we want to drill all the holes, right? But our clients will start in the middle because there is additional information that is valuable there. If it's a completely green field and a new discovery, you want to know what is the porosity, what is the fluid saturations, what is the net present value at a very coarse level of that asset. So what I'm saying is that there's additional layers of information and value that are present even in a well that does not maximize uncertainty on the footprint. And we have limited insight into how operators actually make their decisions because it's very proprietary.
Yeah.
But the exploration and appraisal programs take all that into account. So my question for you is, can you extend this arbitrarily complexly?
Yeah. Well,
to-
that comes in the next slides, right? Also, I'm
I'll-
consulting now for Schlumberger, so we maybe should talk.
Okay.
Because I'm consulting Schlumberger how they can start doing this.
Okay.
Because the thing is what you said, we can do MPV, we can do volume, we can do this, we can do that. What are you exactly going to do? That's the question. Because if you say MPV, maybe you will drill in the middle, but then you're actually not efficient. So the decision on what you're going to be called, we call in AI, the reward is essential and is an unsolved question. We can't just say, oh, let's drill for everything. It doesn't work like that, right? So we'll get to the more complicated stuff later.
Listen, thank you.
Yeah. Yeah.
Do you revise your EOI once you've drilled the first hole?
Yeah. So this is open loop planning.
Okay.
Yeah. Okay. So open loop planning, because we're going to do open loop planning is reactive, meaning you react to an outcome. AI-based planning, which we get later on, is proactive. It actually tries to figure out what the possible outcome could be to optimize the planning. So that was our kind of first paper that we wrote together with Cobalt on that, and is a very effective way of exploration. We applied it on hundreds of projects. Cobalt is active on 4 continents, hundreds of projects, and we applied it consistently. And what we do is we walk away quicker than anything else. The value is in the walking away. That's not how junior mining companies think.
Yeah.
They think the value is the MPV. See where we're going with this?
Yeah, sometimes it's better to quit.
It's better to quit. Okay, well, you're not acquiring one data point, you're acquiring multiple data. So let's now acquire 2 data, right? Because would you have drilled the first well differently if you knew more boreholes would be drilled? Would you acquire surface geophysics differently, doing standard configurations, knowing you already have a budget for boreholes? That's called sequential VOI, where instead of collecting one data, you have the option to collect a second data. You don't have to collect the second data. It is an option for you. So well, in betting, right, is that you have an option later on to do something. You may do the first thing different. So we can therefore calculate sequential value of information, which is the value, posterior value of collecting with the first type of data, or to continue with the second type of data once we have the outcome of the first type of data. Okay, and that continued value is over here. We will only continue with the second data if the cost of that data is less than the value when acquiring both of them. Again, we need an economic model for this, so we can, I have a case like that. So this is kind of where we come to the walking away quickly, right? So here, the same case, and we have, let's say, 6 boreholes. And here, actually, I calculate the value of information, right? I sort of calculate the value of having if you would have the mineralization. And so you see here, the maximum value is $137 million. It's given by borehole 61. So borehole 61 is this borehole. Notice that the borehole in the middle has the lowest value, 20.3 million. Now we're going to calculate the sequential value of information, which is, what if we drill first any of these, followed by another one? And we see now the first borehole you drill is 33, not 61, followed by 61. This is critical, right? Because now we're starting to do closed loop planning, but only 2 boreholes. Closed loop planning is where you say, I know in the future I will have information somewhere else, and that information somewhere else of that second information helps me in determining where's the optimal location of the first information. That is closed loop planning. Most of engineering is open loop planning, what we call model predictive control, where you do something and then you react. Do something, react. We can also do sequential efficacy of information. It's exactly the same as sequential value of information, except that right now you replace everything with probabilities. And here we have a really nice example We work with a company called Fleet Space. It's a company that does space exploration. They go on the moon, they want to go to Mars, but of course they can only make money on Earth. And so they have these passive seismic sensors. They connect with satellites, which is great because then you can get continuous monitoring. And this is a passive seismic technique. So we're just passively observing the seismic noise, and that passive monitoring can then be turned into an active signal and gives you some idea about the density or acoustic impedance of the Earth. This is a great technique to do exploration of porphyry copper. So porphyry copper is a primary source of copper in the world. The largest copper mine in the world is in Chile. It's called Escondida. And you see here that those copper mines are all along this belt here, called the Laramites, right? And so we have actually a lot of deposits in the United States, except they're locked up in permitting. That's why we're not mining them right now. So how would you acquire that geophysics? Well, number one, we have to do a little change in our notation because now we have continuous measurements, right? The parameter is no more discrete. So we change the sum and we make it an integral. And if you look at it, the value of information now, or the efficacy information looks exactly like the Bayesian optimal design. So Bayesian optimal design is a special case of value of information because I've taken the value of information and reduced it to this equation. So if we do that, there's a lot of equations around that. I want to just show this slide to show that the way you approximate or calculate is Monte Carlo, right? And to do Monte Carlo, there's a lot of stuff in here. There's machine learning of the F. There's all kind of variational methods, blah, blah, blah. I don't know to talk about that. But there's a lot under the hood here to be able to calculate that. So here is an example of where we have the option of acquiring ANT, so ambient noise tomography. These are the sensor locations on the surface of the Earth. And you can either have this one, or that one. So the question is, if you calculate efficacy information, it's likely that this is the best one. Now the question now is, what if the next thing we do is a borehole? I already have money for a borehole. Schlumberger is ready to come in with their trucks and start drilling. Would you still acquire any of these, right? And now comes your question is, what is the objective? Is the objective to know the volume of the porphyry copper? Or is the objective to know the location? Or maybe I have another objective. I can have 5 objectives, right? When you have more objectives, the decisions will change. So here we thought, well, knowing how big it is and knowing where it is seems pretty good, right? And so we want to maximize this as well as maximizing that. And so what we see here is that the dense ANT together with borehole 3 gives you the best sequence of information. However, the median one, it's not that bad either. So now you can start, I want to trade off a little bit of uncertainty reduction with cost. And you can observe that, right? You can trade that off here. We would never just first drill, that's not good. And we would never first do ANT. We see the ANT tells you the volume, the boreholes tell you the location. If you combine that with that in a sequence, you get that.
Great.
Yeah.
How deep NT can sort of penetrate or get information?
Oh, that's a good question. I don't know, there's no numbers on here, but for example, in Australia, you have a cover. This is why ANT is so interesting. You have a regolith with a slow acoustic impedance. And I think this goes about 500 meters, something like 400, 500 meters. Yeah. You monitor for a long time.
I see.
So through the passive, you acquire a surrogate active material. That's how they do that.
So the sensors themselves are just surface.
Yeah, they're just at the surface. Yeah. But you need to know, you need to determine the geometry, right? And you don't know yet. The only thing we may have is gravity. right? So the gravity anomaly can tell you something about what's there, but it's very fluid, it's very uncertain. Okay, so that's nice. These are kind of toy cases. But real exploration involves planning many, many, many things, not just two. Possibly hundreds of boreholes. Hundreds of boreholes, if a borehole costs $1 million, that's 100 million. Junior mining company does not have 100 million, they have 3 million. So they drill two. Where did they drill the two? Smack in the mineralization, because then they could go to the bank and say, we found more mineralization, right? It's not good business. That's basically, there's a lot of things that are questionable. So the problem, however, of large sequences of information is a problem that is formulated and solved in AI. A self-driving vehicle, I don't know, they're driving in Boston already. We have about 10% of our vehicles are self-driving vehicles in San Francisco. This is the future, right? Self-driving vehicles are, what are they? They are agents that make sequential decisions under uncertainty, right? They go, they have to plan, they have to do some planning ahead and something training ahead. This is called offline training. And as they're executing, they have to do online adapting, which is called closed loop planning. And what do? They look for information, LiDAR, radar, and whatnot, visual, and they try to reduce uncertainty on what they see in the road. That is a self-driving vehicle. Exploration, exactly the same. So an intelligent agent, they may have heard about agentic AI, this is kind of hot right now, is an agent. There's a computer program that can perceive the environment, make decisions, and take action autonomously to achieve a set of goals in a certain time framework. And so the sequential decision-making is called Markov decision processes. And the way we then add uncertainty is reinforcement learning, which is not very applicable to our problem because of computational issues and other issues. Partially observable Markov decision processes is what we'll talk about. So I'll give you a quick tutorial on that of sequential decision making. Let's say you want to drill in a formation, right? Schlumberger does geosteering, and you want to stay in the formation and say that is your thing. How would you go? That is a Markov decision process, right? You make a decision, you make another decision, etc. However, there's a possibility. So the goal is to obtain what we call a policy. A policy is an action of the next step, which is function of the previous state of the system, which is where you are now, and the previous action you take. So that's a policy. So a policy is something that we want to optimize for. And then we have our return, right? A return is to get, of course, to the output and to get closer every single time. So that is called a Markov decision process. There is now an action, something we do in the real world, a reward that we get out of that action, and a state which constantly changes as we are taking actions. There's however, a problem. That is the action you execute may not be perfect. When you drive with your car and you want to turn right, you're not always getting right. There's a possibility that things are not working out. That is called a transition function. There's a possibility that you want to go over there, but you end up over here. There's a mistake. So that's a probability. It's called transition probability. So the person who solved that, again, there's a lot to say about this, is Bellman, who came up with basically this idea of dynamic programming to solve this. So dynamic program is a general technique, as you know, in computer science, but was invented basically to solve these kind of problems of Markov decision processes. And it is a recursive way. So you want to optimize for the policy. The policy is function of some value function or utility, and that utility is recursively calculated. And here you see the function, transition function. Okay, so we can use what is called an offline solver. Is something that an offline solver is something where you solve and you execute. So there's no adapting in the middle. So these solvers under these situations are giving you the perfect solution. But this is not always possible, right? You can imagine in real problems, we can't just solve and drill 100 boreholes and come back the next day and say, okay, everything's great. No, you are going to do online solvers, or we'll talk about in a bit, Monte Carlo tree search, which are techniques that readapt every time you execute. So it was doing that, yeah. So every time you execute, you see it actually made a mistake here, right? Well, the offline solver doesn't have that. What we are dealing with is where you have essentially when you start out, you know nothing. When you make the first decision, you only see black. So that means that as you are deciding, you also have to decide on measuring. So the optimization of the reward does not just include optimizing reward, it includes optimizing the measuring such that you can optimize the reward. So there are two decision problems: deciding what measurements to take and deciding what actions to take. You cannot just say, I'm going to take these measurements and then decide. That is less efficient. So the decision on how to measure is included in that. So you have now a measurement, right? And you see that we are finding the exit, right? You see that we're getting there. So that's called a POMDP. Means partially observable MDP. A lot of math around that. Basically, there's an optimal planning Bellman equation, and there is a Bayes rule. You're adding Bayes rule to the Bellman equation, basically. Solving that is the breakthrough that happened in 2010. And you may have heard about AlphaGo. Who knows Go? Go? You know what happened with AlphaGo? Right? The best guy in the world got beat by the computer. Why? Because the computer was using POMDPs and high performance computing. Right? If you look at your phone, nobody will beat the chess player on your phone ever, right? And that's been proven. So how does this work? So here's your board of Go, right? You see a little bit the board with the Go things on it, the black and the white dots. It has to search for a solution, but to search for a solution, there are two problems. There's a curse of dimensionality, which means there's so many combinations on the board. And then there's a curse of history, which means if you go forward in time, you will get many different observations, potentially. Right? So think about the drilling. It's the same thing. When you drill, there's many possible locations you can drill. And if you go now forward 10 drills, there's many possible outcomes that come with that future drill. And so the Monte Carlo tree search technique, which was sort of deployed then by DeepMind, the Google company, came up with that and solved all the problems. Okay, so you can now see that mineral exploration is a POMDP problem, but with humans in the loop. Okay, so now I come back to our decision diagram. Remember about actions: A, R, S, O, observations, right? You take an action, you drill, but you drill the next one, and you get, however, also observations. You get a borehole where you measure concentration of copper. That can be used to update the uncertainty. But as we'll see in a bit, it's not that simple, because geological uncertainty has an enormous complexity to it. It has structural complexity, concentration complexity, it has many things. And geologists are often very uncertain about the hypotheses they make about the subsurface. And that's what happened here. We used a POMDP method to drill into this area, starting from almost nothing. So you have basically, the company has $40 million to drill. how would they spend this budget? Okay, so I'll show you that. This is in the copper belt in Zambia, bordering the DRC. This is the most prolific, one of the most prolific producers of cobalt in the world. 80% of the cobalt comes from this area. Part in the north has a lot of cobalt, the part in the south has a lot of copper. And so we're drilling in this area over here, where there's nothing. No geophysics, no nothing. There's nothing. However, we know there's a mine over here, and we have some vague structural geophysics. It's not very good because it's gravity. This is very uncertain. But we have a good idea on how these formations were formed. These are called sediment-hosted copper deposits. How does they work? These are deposits that get deposited when, number one, you have a rift, right? An area of the world, this big rift system that creates faults. There are some red beds here which have copper. There are fluids coming down that are chlorinated that starts to do the chemistry here, right? Big chemistry pot mixing, and the copper gets released and concentrated in these fluids. Then these fluids move up the faults, and you have deposition of that fluid over here in thin sediment layers that have pyrite. Pyrite is iron sulfide. The copper replaces the iron sulfide into copper sulfide, which is chalcocite. Chalcocite, 60% copper. That's huge, right? So these layers have up to 18% copper. That's what we drill. That's a huge amount of copper. If you look at the copper deposits in the US, they have 0.5% copper. So mining these have very little environmental footprint because you mine them from the surface and they're very high concentration. So you see now, right? How do we turn this geological idea into an actual three-dimensional model? Number one, faults, but we don't know where they are. Number two, sediment layers. We don't know where they are exactly either. And number three, there's probably some kind of a change in mineralogy. If you go from here down to here, as you start precipitating the copper, you get more copper iron sulfide, like chalcopyrite and other types of mineralizations. So the way this worked is that we sat down with the three best geologists of sediment-hosted copper in the world that already had discovered other deposits. And they said there are two things happening, faults and mineralization. The faults will create thickness, mineralization will create grade. So this is ton, this is volume. However, they don't really know what these domains are, how they are, there's many possibilities. And then within those, you can simulate the grade, right? Which gives a grade, and you can simulate the thickness. And so when you drill, you don't observe the domains, you observe the grade and the thickness. And so we are building what we call hierarchical, Bayesian hierarchical geostatistical models, where we start out with somebody makes an assumption on the nature of mineralization. You see, this is oxide, this is chalcocite, and this is chalcopyrite. But we don't know this, right? That's uncertain. Then in each domain, we have some variability, which is some kind of variability, variogram-based variability within that domain. So you see that the copper mineralization is different within each domain. And so we can generate that. However, we don't know that's true. It could be like this, it could be like that, it could be like that. You come together with, you know, the joke is you come together with three geologists, there are four hypotheses, right? There are actually many more, there are 8, right? And so now the question is, where would you drill? Would you drill to discover grade? Where would you drill? What would you first focus on? You'd focus to falsify your hypotheses. You try to drill to prove yourself wrong. Then you would drill to find the domains. Then you would drill to get the grade. See that whole thing? But to drill to find the hypotheses, that's a difficult Bayesian problem. It's a hierarchical Bayesian problem where the information comes on the grade, and you want to get the uncertainty in the hypothesis, right? That by itself is from. So here are all the hypotheses. It started with 3 hypotheses, right? After a while, they were all falsified. So we had to make some more, 6, right? And after a while, you see that, okay, it starts to stabilize, right? You see, actually, it's after the sort of like in 2024, suddenly we got a lot of information and we had to make more hypotheses. So you see how the human mind is biased, right? When you have no information, we're very certain. When we have a lot of information, we become much more uncertain. Yeah.
Just a quick question. Did you know the locations of faults, at least? You also,
No. Some ideas that there should be east-west, but that's it.
you didn't
No,
find
there's
any
nothing.
surface
No.
features? I see.
No. It's a big problem.
Ah.
Okay, so let's go now. Look, here's the first borehole. You see, this is, this costs money. It's not just a hypothetical exercise on your computer. And so let's now look at this, right? So let's say I am here and I've drilled some boreholes and this is my grade. Okay, you see it goes up to 8%, right? That's very large. This is my uncertainty, right? This is kind of the variance, this is the mean. Where would you drill now? Okay. Most companies would drill over here. They want to know more, right? Okay, so let's see where I'm going to go over this, where it drills. Oh, that's different. That one. The best borehole they drilled was that one. It had no copper. See the mentality change of I want to drill to find copper to one, I want to drill to falsify geological hypotheses. And so if I drill an area that's no copper, what's going to happen? This is now out of the question and everything switches to that way. That's where the efficiency comes. There's no human who's going to do it like that. Right? And so you see, if you look now what's coming, it is like it switches in and out. It goes on the sides and then it goes in the middle. It goes on the sides and it goes in the middle. See? On the sides. So it's found some more on that side, chose the middle. Now it goes there again, low percent copper, and so on. And you see those things going up on the right-hand side? That's a lot of money. Okay, so they opened the mine last week, and I thought this was a beautiful. This is how the world gets better. This is the president of Zambia, and the person is telling him that they are using Bayesian Gaussian process regression with Hamiltonian Monte Carlo. He looks a little puzzled or a little like suspicious, but the world is a better place, right? If the politicians start to look and do AI. Okay. Conclusion, I hope to have convinced you that sequential information gathering is how you plan a budget, that intelligent agents formulate this question using Bayesian principle, but at high-level hypotheses. However, when humans get involved, and this is just normal, prior models provided by humans get falsified, and often very, very quickly. And so you understand also that doing this requires venture capital money, right? You have the right people. You have to put the team together, right? And the success of COBOL is not so much that they use AI, as much that they put the team together. They're using high performance computing on Amazon Web Services and all that stuff, right? You don't just do that, right? And so doing that, having somebody then where the information in real time gets, from Zambia transferred to Berkeley. That's stuff that's not academic. Okay, so little commercial. I have a new book coming out in June, and there were this case and all the details on these cases of how to make decision making using AI, the kind of things that I just talked about. How to even philosophically think about these problems of Bayes and Popper, which is falsification, and then how to build protocols. And this is done for real world cases that are not minerals. There's a case on geothermal, case on groundwater, case on oil and gas, etc. Of course, software engineering and implementation is also something that's very relevant. Thank you for your attention.
We have like a time for a few questions. Here.
Question online?
Yeah, so it's by Smeaton. He or she's asked, do you have to reckon with the uncertainty on the location of the magnetic intrusion?
What's the question?
Do you have to reckon with the uncertainty on the location of the magnetic
Yeah. Yes.
I
intrusion?
think he may be asking about measurement uncertainty and how you.
Measurement
integrate that
uncertainty, yeah, of
any
course, yeah, all
measurements.
these things get included, yeah. It goes in the likelihood function, right? This is standard.
I can allow him to speak if that's okay.
Any other questions? Go ahead.
Is there like a standard methodology for converting the information you get from the borehole into the probabilities that you're inputting into your decision-making process?
So as I said, this is a hierarchical Bayesian problem, right? It means you have your hypotheses. They determine the domains that you have, and they determine the thickness and the grade.
Yeah.
The information you have is on the grade. So the question is, how do you infer from the grade the probability on the hypotheses? And so that requires chain Monte Carlo sampling. Those are not simple things, right? There's a lot under the hood here that are not simple, but that is how it would be done. And so there's a lot of work, I think great work that needs to be done in that area. Number one is, how do you translate ideas on geology, which is conceptual, into actual 3D mathematical models or numerical models? And those models have parameters, right? And those then get used to generate spatial realizations. And then your observations are spatial. But you want to know what that means for everything down that flow. And that is a challenging problem. Yeah, that there's a lot of work to be done there.
I have sort of kind of a little bit philosophical question. I mean, your work is super nice in the sense that kind of bridging fundamental mathematics and actual applications and making money, right? And have you experienced any sort of pushback from like a domain science who might be skeptical
All the
about
time.
AI?
Yeah,
How did you overcome this?
I ignore them. Cobalt metals goes from $10 million to $3 billion. That's the proof.
In how many years?
In 6 years.
Oh, wow, that's amazing.
That's the proof. What more proof do you need?
I see.
Right? So now everyone's catching up.
So that
Everyone's like looking, oh my God. And now you have 5, 6, 7 startups around in this domain. The oil company, the mining companies are looking at that and say, that's right, the way we drill is just determined by a person. Oh, you can do this different. So they're mostly unaware about what's under the hood here. And I think that is the change that's going to happen. The thing we have to realize a little bit is that the mining industry is being thrown into this energy transition. And they were previously mining iron and coal and gold, right? Now they have to do something that actually requires significant science. And they are not used to that. And so they're kind of stuck a lot in deterministic, heuristic, expert-driven stuff.
Okay, thank you. Hey.
Yeah, good talk. Thank you. I was wondering, like, you're talking about uncertainties, grades, a bit of geology. I just wonder if those predictions, how much geology actually plays into those decisions in these models.
A lot here. Yeah. So as I said, you have the sediment hosted copper people who have worked on similar deposits across the border in the DRC, have made discoveries. They are in the room. So I've been in these rooms for 2 days. The Kurt House, the CEO, locks everybody up, and everyone's in the room. The computer scientists, the data scientists, the meteorologists, everybody, and the geologist has to explain to other people what geology is. And I tell you, that's the hardest part, because geologists like to be, hand waving a little bit sometimes, and so that is where the money is made. It is in the what we call the epistemic uncertainty. That very high level uncertainty where you have no even idea of how things look, right? And so they come up from their experience, but their experience is descriptive. So turning out the descriptive into the actual 3D models, that's another big jump that very few people work on, because it's not an academic problem in a way, right? It's a practical problem of how you do that.
Do you think AI can replace those
No,
geologists
absolutely
eventually?
not. No, that's
Totally
ridiculous.
Question?
Swing want to talk, yes.
Go ahead.
Yeah, can I go ahead?
Yes.
Thank you, Jeff. Excellent talk. I'm from Schlumberger, ex-Schlumberger, retired last year. And I want to go back to the question of the quality of the measurements and the quality of the inversions. So my colleague who's with you there, Jeff Miles, spoke to the uncertainty around the measurement. If you could elaborate a bit on your experience so far with the quality, not just of the measurements but also the inversions.
Yeah.
This is something that within Schlumberger we believe actually could reduce tremendously the uncertainty. So how critical it is, and how do you incorporate it?
Yeah, absolute. The biggest need for research is Bayesian multiphysics inversion. Doesn't exist. So we work with a company called Excalibur, or the company that is acquiring pretty much countrywide geophysical data. And so they acquire a whole suite of data, right? So typically mag and gravity and then time domain EM. And so most of the standard workflow is to do deterministic inversion. But the problem is, unlike seismic, there is such a large uncertainty around, number one, the petrophysical properties, which are not measured ever. So it's not like the oil and gas industry where you have a great database around sandstones and shales and their petrophysical properties. They don't have that. So that's one big problem, is we have to measure those and measure those accurately. The second one is that the inversions are all deterministic and they are smooth inversions. So everyone looks at the map and says a big anomaly, but the big anomaly is created by the smoothness of the inversion. It's not necessarily created by the geophysical data itself. And so therefore, what we're trying to do is Bayesian multiphysics inversion, which is of course challenging, where a lot of AI has potential, in particular around surrogate models for all of these forward models. But then also the methodology of being able to integrate real geology into those inversions, such like, if you remember the porphyry copper case, we have actually a good idea of the various chemistries of these porphyry copper, and potentially they have some relationship to acoustic and other properties. But again, we need to have more information on that. So I think more information on the petrophysics, more higher confidence, borehole imaging, therefore, and just uncertainty in inversion, and do it multiphysics. Three things that really aren't done much.
How deep are the boreholes that you have to consider in this for critical minerals?
Oh, they go. The mine is 1,500 meters, but they drilled up to 2,500 meters.
Okay, thank you.
The last question. Yes, go ahead.
Hi, nice talk. So the question I want to ask is that I understand you want to do the sequence of decisions and you want to choose the best possible actions from action space. But I guess my question is that you basically have near infinite number of actions that you can choose, because you can choose different GPS locations, you can choose how deep you drill, you can choose the angle you drill. So you mentioned AlphaGo.
Yeah.
You also mentioned human in the loop. So which kind of methodology is actually used in choose the best possible?
So the humans provide the prior models. Basically, they say, here's a hypothesis, here's the numerical models, here's everything. And so the input to that drilling program is 100,000 geological models.
Okay.
The program is doing the computation to determine the actions. There may be some constraints around where you can drill and things like that, environmentally and others, but it's the computation that is deciding the action based on the input uncertainty.
Okay, thank you so much.
Okay, thank you.
Yes.